Okay, so in this next video we're going to tackle another problem involving bivariate probability distributions. Okay, so the problem is this. Let's say you have some interval, let's say you have an interval 0 to 1, here we are, and basically you have two little people, so person X, let's say person X is the blue pen, and person X has to pick a point, so he can go here, let's say, and person Y also has to pick a point here. So person X picks a point and person Y picks a point. So they both pick a point between 0 and 1. And basically what we want to calculate is what is the expected value of the distance between person X and person Y. So we want to work out what is the expected value of, let's say, person X's position minus person Y's position. Okay, so the way we can think about this is we can think about it as being the same. We can think of the sample space as being the same as what we've been dealing with for many videos now, which is a square. We can think of it as being a square, and basically all what we can do is plot person X's position on the x-axis and plot person Y's position on the y-axis. So if person X picks somewhere dead on the centre, so person X picks 0.5 as his position and person Y picks a quarter, then the point that would correspond to is this point here. So all possible outcomes of this experiment is effectively analogous to all possible ways of picking a single point from this square. So basically we can then set up two random variables, x, which is going to ascribe, which is going to take any point here to the value, well, to the it's going to give you the x component of your position. So it's going to give you the position that person X chose, so it's going to ascribe you a number between 0 and 1, and this is going to take you to, so it's going to take any outcome to, let's say, person X's position, and then we've got another random variable, let's say Y, which is going to map you again onto the interval 0, 1, and it's going to ascribe to every point here, it's going to ascribe the point that person Y chose. So it's going to again go between 0 and 1. So this point here, which was 0.5, 0.25, x is going to map this onto 0.5 because 0.5 was the point, was the value that person X chose, and it's going to Y is going to map it onto 0.25 because that was the value that person Y chose. Okay, so what we now want to know is what is the expected value of the modulus of x minus y. Well, what we can do is think about this as a joint random variable, xy, which is mapping you onto R2. It's specifically mapping you onto 0, 1 cross 0, 1. So it's describing you an ordered pair in that square of of R2, so this is the square of R2, and it's ascribing each point of this square a point in this square of R2. And then what we can think of as doing is we can think of having a function, let's say g of xy, which is going to ascribe to each of these ordered pairs. It's going to ascribe you the modulus of x minus y. So if we have an outcome over here, let's say s, it's going to be mapped onto some point in this square of R2, which is x of s, y of s, and then what we're going to do is this function here is going to map it onto the real number. It's going to map it onto a real number, and the real number it's going to map it onto is the modulus of x of s minus y of s. Okay, and what we want to work out is what if we view this now as the random variable z, then what is the expected value of z, i.e. what is the expected value of the modulus of x minus y. Okay, and by the law of the unconscious statistician for bivariate distributions, this is just equal to the integral from negative infinity to infinity of negative infinity to infinity of the modulus of xs minus ys, modulus of x minus the modulus of y, rather, because we're integrating over R2, times the probability density function, which we know from previous videos is just equal to 1, because this area is equal to 1, and it's going to be a uniform distribution, so it's just going to be 1, because if we integrate 1 over that region, it's going to sum up to 1, which is the correct requirement for a PDF. So we're just going to get 1 dx dy. Okay, so the first thing is we can cut these limits down, because we do not need to sum from negative infinity to infinity, negative infinity to infinity, because this PDF is only 1 on this square. It's actually 0 everywhere else. So on all the other bits, the integral is just going to be 0. So in fact, I should have put in the joint PDF of x and y as a function of x and y, because of course it is only equal to 1. It's equal to 1 if you're an element of this box. So 1 if xy is an element of, let me just call that region R, oh dear, R, and 0 otherwise. Okay, so if I put that in, then this reduces to the integral from 0 to 1, the integral from 0 to 1 of the modulus of x minus y dx dy. Okay, that's excellent. So now this problem of computing the expected value just reduces to the problem of taking this double integral. Now, the problem is that we have this modulus function. And the modulus function, remember, is going to flip values if they're negative, and it's going to remain the same if they're positive. So let's think about this integral. We are integrating over the region 0, 1, cross 0, 1, so this little square here. Now on this square, the modulus of x minus y. Now the line x is equal to y here will have value x minus y equal to 0. So on this line here, on this line here, this diagonal line, the value of this function is going to be equal to 0. If you go to the right of this line, i.e. if you are in this blue triangle down here, then x is going to be bigger than y. So if I take any point here, the x component is going to be bigger than the y component. So this x minus y is going to be positive, therefore, and the modulus of x minus y is just going to equal x minus y. Conversely, on this triangle over here, the x component is smaller than the y component. For any point in that pink triangle, x is smaller than the y component, so x is less than y, which implies that x minus y is less than 0, so the modulus of x minus y on this pink triangle is going to equal negative of x minus y, i.e. you're going to flip the sign, so it's going to equal y minus x. So what we should do is we should split this integral into two parts. Firstly, the integral over the blue triangle, and then the integral over the pink triangle. So let's do that. Okay, so let's say that the integral from 0 to 1, 0 to 1 of the modulus of x minus y dx dy is equal to the integral over, let's say, the blue triangle. So the integral of the blue triangle, so if I get my picture back, it's down here. So the integral of the blue triangle there of the function x minus y dx dy plus the double integral over the pink triangle here, so the pink triangle, of y minus x dx dy. So now all we need to do is compute those two double integrals. So let's start with this one here. So the integral over the blue triangle of x minus y dx dy. So we need to turn this into an iterated integral. So we can think firstly of integrating over dx. So let's firstly imagine integrating over dx. So let's say, well actually sorry, I'm going to let the outer integral be the integral over dx. So I'm going to say, let's integrate from 0 to 1 dx. Now all we need to work out is what we're actually integrating inside. Well, we're going to integrate, we're going to integrate x minus y, and we're going to integrate it dy, but how big or what are the limits of integration going to be in this case? Well, they're going to depend on x, because we're going to, the height on which we go to is going to be a function of x. So we're going to go always from 0, but how high are we going to go up to? We're going to, that's going to depend on your x height, so you're going to go up to the height x, and the reason is that if you look at this blue triangle, we're integrating from 0 to 1 over x, but what do we need to integrate up? We need to integrate the integral of y, integrate this function from 0 to x. So we want to integrate up something that's already been integrated from 0 to y, so that we integrate over the whole blue triangle. Okay, so this is the integral from 0 to 1. Now let's do this integral. If we're integrating dy, so we get xy minus y squared over 2. So you view x as a constant, so this anti-differentiates to xy, and this one differentiates to minus y squared over 2. We then need to evaluate between 0 and x, and we then need to integrate that dx. Okay, so let's go up. Okay, so now this is going to equal the integral from 0 to 1 of x squared minus x squared over 2 minus x times 0, so x times 0 minus 0 squared over 2. So this is all 0 here, so that just goes, and we end up with x squared minus x squared over 2, which is just equal to the integral from 0 to 1 of x squared over 2 dx, which is now, if we perform this integral, we get x cubed over 6 evaluated between 0 and 1, which is just equal to a sixth. Okay, so that's that integral over the blue bit. Now we need to do the integral over the pink triangle. So if we bring down our picture again, so we're going to integrate over that pink triangle, and we're going to integrate the function y minus x in this case. Okay, so the double integral over the pink triangle of y minus x dx dy is what we're trying to compute. Now, this time, the most natural one to do last is the integral from 0 to y. So if we integrate over 0 to y, that's the more natural one to do, and then we'll alter the limits of integration for the dx one. So we'll integrate from 0 to 1, and then we want to integrate from 0 to what value? So let me just firstly write that we're integrating dy there. Now we're trying to decide, we're integrating the function y minus x dx, and we need to work out the limits of the integration. So we need to integrate from 0. In the case of x, we need to integrate from 0 to, where do we need to go? We need to go to where do we need to go to? Y. We need to go to y. So we're integrating over y, 0 to 1, and what we want to integrate is we want to integrate over y the integral over x from 0 to whatever this point is, and that point is y. Okay, so if we compute this inner integral, we get that that is equal to, just by the second fundamental theorem of calculus, you hold the y as though it were a constant, and you get yx minus x squared over 2, again evaluated between 0 and y, and it's completely symmetric. So it's completely the same problem, effectively. So you get the integral from 0 to 1. If you evaluate this, you get y squared minus y squared over 2, and the other bit is just 0, dy. So we're integrating y squared over 2, which just gives us, sorry, I'll move this up, which just gives us y cubed over 6, evaluated between 0 and 1, which is again just equal to a sixth. So if we add these two integrals together to get the overall integral, then we get that the expected value of the modulus of x, the modulus of big X, the random variable x, minus y, so the expected value of that function of the two random variables is just equal to a sixth plus a sixth, which is equal to a third, which is quite an intuitive result. If you had to pick a point, if you were to think about picking a point between 0 and 1, so if you just pick a point for x and then you pick a point for y, you'd expect the difference to be about a third. Okay, and in the next video we're going to see another way to arrive at this result.